So yeah, so we are going to talk about designing vertical curves. And, the way we design vertical curves is through, by using these equations, right? These equations, if we solve for these equations, we can find how the elevation of the points on the curve is related to the x coordinate of the curve location, right? So x coordinate will typically represent the horizontal positioning of the point, and then the y coordinate will typically represent the vertical coordinate of the point, or vertical location of the point that we are trying to define. Now, in these equations, the way we do these is the typical equation, and this is equation 7.3 from your textbook. Y is the roadway elevation, right? So it's the elevation from a random sort of datum point, typically the sea surface, right? So we typically define our elevations on any of the roadways. If you pass through any of these grades in the state, you will see, hey, Cuesta grade elevation, whatever, right? So those are defined based on the sea level, and then you go up from there. And then this Y is typically the roadway elevation measured from that sea level. Now, X is completely different in this equation. The way we define X is that we say the X will be equal to 0 where our vertical curve begins. So if you recall from the last lecture, where our vertical curve begins is right here, right? So if you go back to the lecture here, if you go back here, this is where the vertical curve begins, right? So this PVC. So the X value, if you are solving these vertical curve problems, the X value would always be 0 at the PVC. PVC is the point of vertical curvature. This is where your curve begins. And at that point, the X value would always be 0. And then this Y values get defined. Y value are defined by the elevation of any given point on these curves, right? So any point you take on the curve, the elevation of those points is defined by the Y values, okay? And then if I told you that X value is equal to 0, X coordinate is equal to 0 at PVC, let me ask you this. What will be the X coordinate at PVT? Okay, so if I ask you, what is the X coordinate at PVT? What would be the X coordinate at PVT? If X coordinate is 0 at PVC, what will be the X coordinate at PVT? Yeah, L, right? It will be L because you measure the X coordinate along the horizontal plane, right? Along the horizontal plane. So you can see the X coordinate here will be L. If you're talking about the PVT, X will be L. And then the other thing is that these G1 grade and G2 grades, the upgrade or the downgrade, they are useful as well in figuring out some of these elevations. And I've talked about what these grade means, right? So we know that if G1 is equal to, let's say, 5%, what does that mean? That means if you go 100 feet horizontal, you'll go 5 feet vertical, right? So that's what that 5% grade means, is that if you go 100 feet horizontal, this will be 5 feet, right? So this is what the grade level means. And if it's a negative grade, then obviously if G2 is negative 3%, if you go 100 feet horizontal, you'll go down by 3 feet. Okay? And sometimes knowing this can also be helpful in finding out elevations of different points. For example, if I want to find out, if I'm here at PVC, and I want to find the elevation of PVI, okay? If I'm here at PVC and I want to find out the elevation of PVI, the way we do it is just apply this initial grade G1 to the horizontal distance L over 2, right? So if we have this grade level G1 and then this horizontal distance is L over 2, we can use this horizontal distance times the grade that's here to find the elevation of PVI, right? And then if we know the elevation of PVI, I can get the elevation of PVT as well, because if I know the elevation of PVI, I can use this G2 grade coming down and subtract from PVI L over 2 times G2. Okay, and I could get the elevation of these different points on these curves, especially for PVC and PVT. I can use the slope of the tangents to figure out what those elevations are going to be. Okay, and we'll do an example of that, but I just want you to be aware of that. Like, yes, equation that we are going to talk about is going to be important, but even beyond the equation, you need to know that you will be able to derive, elevations of these points using the horizontal distance and the grades as well, at least for certain of these points. Okay, so let's go back to this equation deal. Let me. So this equation is only applicable, by the way, for points on the curve. Okay, so this equation, y equal to a plus bx plus cx squared, that's your, standard quadratic formula, quadratic equation, I should say, standard quadratic equation. And that quadratic equation defines a parabolic relationship between y and x, right? We all know that. And knowing that, we just have to figure out what these a, b, and c parameters might stand for. So let's kind of think about these one by one. If your equation is a plus bx plus cx squared, where x equal to horizontal distance from PVC and y is the elevation of the curve, okay, let's try to figure out what these parameters a, b, and c represent. So my x and y, if I think about these two terms, x term and the y term, those are my variable for this equation. Okay, and a, b, and c are the parameters of that equation. I hope you know what those mean, right? So a, b, and c don't change in any equation. On a different equation, just gives you, if you take different values of a, b, and c, you just get a different equation then, right? For the same equation, your variables change, your parameters are constant, right? So you're trying to figure out what those parameters mean in any given equation. So if you plug in x equal to 0, I told you what point does that represent? That represents PVC on the curve, right? At x equal to 0, you're talking about PVC, right? Point of vertical curvature where the curve begins. So if you plug in x equal to 0 here, y will be equal to a. So that tells me that if I have y equal to a, that tells me that the parameter a here, always defines what? It defines the elevation of the PVC. Okay, so this is something that I'll note that, and I have that on the slide as well. A is the elevation of PVC in feet. Okay, because if I plug in x equal to 0, I get y equal to a, and that point represents PVC. So I can just say this a is elevation of PVC. Okay. Now let's think about this quadratic equation. If you remember, maybe from Algebra 1, I don't know, maybe some of you were, some of you took it in, I don't know, maybe 8th grade or something. So it's been probably a while. But if you recall that discussion around parabolic equation, one thing about parabolic equations is that if you take the slope of this parabolic equation, okay, you will see that the slope equation would be linear in form, right? So if you do y equal to a plus bx plus cx squared, but now you do dy over dx and take the derivative with respect to x and trying to find the slope of this equation, you will get, so this term does not vary by x, so the derivative of this term will be 0. This will be bx. What will be the derivative of bx? Just b, right? Plus, what will be the derivative of cx squared? 2 times cx, right? 2cx, right? Now, let's think about the slope. And if you plug in x equal to 0 here in the slope equation, what happens? So dy over dx, if I want to find that value at x equal to 0, what happened at x equal to 0 is just b, right? Because 2cx is 0. Because if I plug in x equal to 0, then I get the whole thing to be 0. And then I get slope at x equal to 0 is b. So now let's look at that equation, or let's look at any of these parabolic curve here. X equal to 0 we know represents PVC here, right? So we know x equal to 0 is this point right here, right? So this is your x equal to 0 point. What is the slope at that point? What is the slope when your curve is just beginning? What's the slope? The initial grade, right? The initial grade that you're starting your curve with is the slope there, right? That's G1. So that's why we can say that this B value, this B parameter will always be equal to the initial grade on the tangent, initial grade on the parabolic equation. Now this last point, or finding out what C means, is the most interesting thing for me, because that will also explain to you why we use parabolic curve to do this transition between upgrade and downgrade. Remember, the big picture here is that we are trying to find how we transition between the upgrade and the downgrade, right? So that's what we're trying to do. We're trying to do the transition between two different slopes, okay? A smooth transition between two different slopes. And think about what happens. How can you find C here, right? You can find C if you take the second derivative of this equation, and the second derivative of this equation will be d2y over dx squared. So I'm going to do second derivative, and I'm finding that second derivative, and then it'll be 2 times C, right? If I take the derivative of the original slope that I just got, it'll be just 2 times C. Does that make sense? Right? Now, what does the second derivative represent? It represents the change in elevation or the rate of change of slope, right? How is the slope changing? So this was the elevation. This represents the rate of change of elevation. And this was the slope. So this second derivative represents the rate of change of grade, right? Now, this rate of change of grade is very interesting. It's just 2 times C, right? What's so special about this? Do you notice anything special about this? 2C. It's just 2C. Anything that you note? Yeah. What's that? It's not even linear. It's basically a constant, right? It does not change with x. You see that? It does not change with x. And therein lies the reason why we use these parabolic curve, because it helps you achieve the transition between one grade to the other in a smooth manner, so that the rate of change of grade that the drivers experience as they drive through that curve is always the same. It's not, it's not giving you any rate of change in slope. It's not like when you enter the curve, the slope is changing at a higher rate than when you're exiting the curve or anything like that. The rate of change of grade is always a constant, does not depend on x. And that's a good property to have in the curves that you're using for transition. Okay, so remember this, right? But then the rate of change of grade is constant. Rate of change of grade over x is constant. But you can also think about what that means. If you look at this, 2 times C is what the rate of change of grade is, right? So that's why I said 2 times C is the rate of change in grade. But you can also derive the rate of change in grade using one more little approach by looking at, on an aggregate level, what's happening, right? What's happening on that aggregate level? And what's happening on that aggregate level is that you're going from G2, you're going to G2 from G1, right? So final grade minus initial grade. And then if you divide that by the horizontal distance that your curve covers, right? If you do G2 minus G1 over L, right? So if you do this, and I want to make it bold here. If you do this, G2 minus G1 over L, what you will see is that that's also a rate of change in grade, right? Because you're finding out on an aggregate level, but it's constant. So it's 2 times C. So 2 times C gives you, so you can use this formula, 2 times C equal to G2 minus G1 over L. Okay, so that's another formula that can help you derive the value for C, because, or you can say that if you want to just derive the parameter C, it'll be equal to G2 minus G1, okay? And then you do divided by 2 times it, right? So you can just divide that by 2L. And then that gives you the value for the parameter C. So now what we did here in just a few minutes here, we've been able to derive what A means in the context of the curve, what B means in the context of the curve, and what C means in the context of the curve. So in any problem, in most problems, you will be able to derive the value for A, B, and C either directly, right, based on the given information, or maybe based on one variable. And that's kind of what you're after. So these 3 formulas, like A is the elevation of PVC, so this one right here, and then B is the slope of the tangent, initial tangent, and then that will be equal to G1, I could say, right? So B equal to G1, right? So, and then 2C or C equal to G2 minus G1 over 2L. So if you can kind of think of what I bolded there, you will be able to solve most problems that require you to use the parabolic curve equation. So let's see what, like, one example here and try to solve it. So the problem we're trying to solve now is that we have a 600 feet equal tangent crest vertical curve or sag vertical curve. Okay, there is a 600 feet equal tangent sag vertical curve. It has the PVC at station 170 and the elevation at 1,000 feet. Okay, so the PVC, you know a lot about the PVC. The initial grade is negative 3.5% and the final grade is 0.5%. Okay, determine the elevation and stationing of PVC, PVT, and lowest point on the curve. Okay, we haven't talked about lowest point, and we will in just a second. But let's think about all the things that are relevant in a sag vertical curve, right? So go back to the sag vertical curve equation here. So some of the things that are relevant here, one is G1, the grade, G2, length of the curve, L, and then for PVC, the X value. PVC is always X equal to 0. So elevation of PVC. Okay. And then elevation of PVC, PVI, and PVT, all 3 critical points, right? So you might be interested in those as well, right? So G1, G2, L, elevation of PVC, PVI, and PVT, okay? And then based on these, we can probably derive what A, B, and C are for this curve, and then we'll be able to solve the problem. And I'll talk about the highest point or lowest point in the curve in just a second. Okay, so this is the point we are talking about. Can you tell me, by reading through this problem, what are some of these values that are given to us in the problem already? Do we know what L is in this problem? Yeah, 600 feet, right? Yep, that's exactly right, 600 feet. It says 600 feet is the length of the curve. It doesn't quite say that. It says 600 feet equal tangent sag vertical curve. That means it's the length, 600 feet. G1, we know that it's negative 3.5%, right? The grade into the curve is negative 3.5%. G2 is positive 5%. Determine the elevation and stationing of PVI, PVT, and lowest point on the curve. Okay, so they want us to find out the elevation and stationing of PVI, PVT, and lowest point on the curve. Okay, so let's think about each of these things. Do we know elevation of any of these 3 points? Is that given to us? Yes, because it's given that elevation of PVC at station 170 plus 0, 0, and I'll talk about station in just a second, but the elevation of PVC is given to us to be 1,000 feet. Okay, so 1,000 feet. And then have we used, okay, so only one piece of information that's not yet on the board is the stationing business, right? The station is given to us as 170 plus 0, 0. So what does that mean? What that means is that it's a way of communicating sort of the X value or the horizontal positioning of any point on a curve, or any kind of, not just on a curve, but any kind of roadway alignment, right? So stationing is a way to represent the horizontal location or the, the horizontal positioning of any point on the curve. And typically the station will reset, at least in California, the way we do it is that we reset these stations at typically the county boundary, right? And so you can think of that as sort of like a mile marker of sorts as well, right? So now the way we measure it is that one station is equal to 100 feet. Okay, so if anybody says like, stationing, you should always know that in English system, the unit system that we use for roadway design in the US is one station is equal to 100 feet. Okay. Now this does not, the stations directly do not represent the X coordinate on the curve, right? So if you think about the equation of the parabola, the X coordinate does not represent the stationing at all. Okay. Station is just measured from, just like we measure the elevation from sea level. Think of that as that there is a point somewhere, could be a county boundary line or whatever it might be. You don't have to concern yourself with that. But just from some arbitrary point, this point is 170 plus 00, or 170 times 100, because one station is 100 feet. So this point is located about 17,000 or 17,000 feet from that reference point, whatever that reference point might be. Okay. But that does not mean the X coordinate is for PVC is 170 plus 00 or 17,000. It only means that, the X coordinate is based on what we defined here, right? So we are always going to define X as distance in feet from the beginning of the curve, right? So we'll always use this. So let's see. So let me ask you this. If I write the equation as y equal to a plus bx plus cx squared, let's figure out what we need, what we know about this equation. Okay. If I want to find, do I know the value for a here? Do I know the value for small a? Right? Small a is elevation of PVC. If you look at the problem here, or if the, what we defined as a, it's the elevation of PVC in feet. So in this case, a will be equal to 1,000. Right? So we know that a is 1,000 feet because a is the elevation of PVC, and that will be 1,000 feet. Now, do we know B? Remember what B was? If you remember, B was the slope of the initial tangent. Okay, so is B equal to 3.5, negative 3.5? Not quite. It's remember, if you look at the units that I provided to you before, B is the slope of the entering tangent, but I want to measure it in feet per feet. I don't want to measure it as a percentage. So my B value, in fact, will be equal to negative 3.5 over 100. Okay, so I know B as well, or 3.5%, and I should enter that as negative 3.5 over 100. Okay. Now, C is a little bit of, it takes a little bit of a calculation to do, but it shouldn't be very hard, because C, we know according to our formula, is 2 times C is G2 minus G1 over L, which is the rate of change of slope. So C will be equal to G2 minus G1 over 2 times L, where G2 is 0.5 over 100, 0.5%, minus G1, right, over 2 times 600. Okay. So my my value for C can be obtained in this equation by doing G2 minus G1, G2 minus G1 over 2 times L. Okay, and I could solve this. It'll be 4 over 100 times 2 times 600. And if I do that, so it comes out to be 1 over. So yeah, it'll be what is that? 1,200. 1 over right? Something like this, right? So you could figure out what C value is going to be by simplifying this expression right here. Questions? So it's G2 minus G1 over 2 times L, and 0.5 plus that will be 4 over 100, and then times 2 over 600. So if you were to solve this, this will be this value here. Can somebody verify the math here? Make sense? Yeah. Okay. Thank you. All right. So yeah, 4 zeros and. Okay. So now that you know A, B, and C, you can figure out any point, whatever they're asking, you can now figure it out, right? Once you know the equations of A, B, and C, if you know the X value, you can figure out the Y value. So for example, if I were to do this, if I were to figure out, okay, they're asking me for elevation of PVI and elevation of PVT. So my equation then becomes Y equal to, A, I know A is 1000, right? Minus 3.5 over 100 bx times x plus cx squared, which is 1 over 30,000 times x squared, which is, I'll just plug in x squared, right? So I just put in x here and x squared here, right? So it's, what I've done is I've put the values for A, B, and C in my equation, and now I'm ready to solve it. Now, my question to you is, the first thing they're asking is, determine the elevation and stationing of PVI. So let's worry about the elevation first, okay? If I want to find the elevation of PVI, what do I do? What do I plug in X value as in this equation for elevation of PVI? So let's write down, first thing I want to find is elevation of PVI. What will be the X value at PVI? L, PVI. L over 2P, because remember, it's a sag vertical curve. And they're all equal tangents. So we know that this is always going to be PVC to PVI is going to be L over 2. And this is going to be L over 2 as well. And this is my PVI, right? So I know that at PVI, X equal to L over 2. So should I just go ahead and plug in X equal to 300 here, because my L is 600. And we know that in this problem, L is 600 feet. So should I go ahead and plug in L equal to 300, I mean, X equal to 300 feet in this equation to get the elevation of PVI? No, that will be completely incorrect. You know why, right? Because PVI is not a point on the curve. This equation does not define the elevation of PVI. It only defines the elevation of points that are on the curve, that are located on the curve. PVI is an imaginary point where the two tangents would have met had you not designed the curve at all, right? So that's why elevation of PVI has to be obtained not using the curve equation. You cannot use the curve equation to estimate the elevation of PVI. Okay, let me ask you this though. If I was looking for elevation of PVT instead, if I was looking for elevation of PVT, could I use that equation instead? Yeah, if for elevation of PVT, I could have put in, for elevation of PVT, go ahead, put X equal to 600 and solve it. You will be in good shape, okay? Right, for elevation of PVT, the last point on this curve right here, so this is your PVT. For this point on the curve, yes, because this is a point located at the end of the curve, you can put in X equal to 600 and be able to solve for the elevation of PVT. So let's go ahead and find the elevation of PVT first. Okay, elevation of PVT first by plugging in X equal to 600 into this equation and give me what that value comes out to be. Okay, so we're trying to find the elevation of PVT. I took out the I, right? So this is PVT now. And then that'll be Y at PVT will be, Y of PVT will be 1000 minus 3.5 over 100 times 600 plus 1 over 30,000 or 600 squared. 600 squared divided by 30,000. Right? And let's see what that comes out to be. Whenever you have the answer, please let me know. And I'll make a note here. Can't use the curve equation to solve for PVI elevation. Okay? Okay. So just remember that you cannot use the curve equation for the PVI elevation, but you could use that for PVT elevation. Does anybody have the value here? 991 feet. 991 feet could be right. Yeah, 990. Okay. Okay, let me crowdsource it once again. 991 feet. Is that okay? Looks good for a few other people. So yeah, so that's right. So you got the elevation of PVT to be 991 feet. So for elevation of PVT. Okay. Now we said we cannot use the elevation of, the curve equation to get the elevation of PVI. So what can we use? You can use the slope of the initial tangent. It's negative 3.5%. So you know how far down do you come? You come down 3.5%. Every 100 feet, you come down 3.5 feet. And this distance is 300 feet. So L over 2, we know is 300 feet. So elevation of PVT or PVI will be 1,000, right? So because the elevation here is 1,000 PVC, 1,000 plus negative 3.5 over 100 times 300, right? Because every 100 feet, you go down 3.5 feet. So how much farther down would you go in 300 feet? This is what this term represents, right? Negative 3.5 over 100 times L over 2. Does that make sense what we are doing here? We're using the slope of the tangent, negative 3.5%, to get the elevation that we know here, to get it over here along this tangent. So this box part represents how far down would you come if you travel 300 feet horizontal along this tangent. Okay. So what's the elevation of PVT or PVI? Let's calculate that. Well, so use initial tangent slope, right? Use initial tangent slope, right? And then elevation of PVC. So what's the value? Anybody have value for me? Should be pretty easy. 10.5 feet, 989.5, right? So the answer will be 989.5 feet. If you solve this, you should get 989.5 feet. Now, there is, we haven't talked, so we've talked about PVI, PVT. And let's quickly talk about the stationing deal as well, right? So stationing is pretty simple. Stationing is one station is equal to 100 feet, right? So that means 300 feet is equal to 3 full stations, right? If you're talking about 370 feet, for example, at any given point, 370 feet, that means it means 3 full stations and 70 additional feet, right? So it's that's how the stationing works. So if you're trying to find the if you're trying to find the stationing, so for stationing, PVC is equal to 170 plus 00, right? So stationing of PVC is 170 plus 00. So stationing of PVI, that's pretty simple. It's 170 plus 00, right? So we write that plus 3 plus 00. And 3 plus 00 basically means 3 full stations, because that's basically 300 feet. Because we know that L over 2 is 300. So this is L over 2, which is 300 feet in this problem, and expressed as stations. Okay. So what I'm doing here to write 3 plus 00, I'm representing 300 feet of distance, 300 feet of horizontal distance as stationing. Okay, 3 plus 00. And if I add the holes, it will be 173 plus 0. Okay, so that's the stationing of PVI. Okay, now let's say similarly, stationing of PVT will be 170 plus 00. And then you're going to add 600 feet, the full curve length, to it, right? So stationing will be 170 plus 6 whole stations, so 176 plus zeros. Okay, so the way we'll write it as 176 plus 00. Make sense? Questions, comments? Yes.
The length of the curve is longer. Do we count that? Or...
No. So this is the thing. In geometric design, in roadway geometric design, we always measure the length along horizontal plane. So anytime you're seeing length being measured, we measure it on the projected horizontal plane, right? So that's why we do not measure the parabolic curve length, right? We always measure X as on the horizontal plane. So all the points are projected on the horizontal plane. So we are always measuring these straight line distances. Now, this will change when we talk about horizontal curves in maybe today's lecture or maybe next week. When we talk about horizontal curvature, the circular curve that we're going to design, they're going to be located on the horizontal plane. So there, when we measure distances, we will have to measure along the arc length of the circular curves. Okay, so we'll get to that point. But when you're talking about the vertical curves, always measure the straight line distances and not along the curve. So we don't measure the curvature. I mean, we don't measure the length of the parabola itself. Okay, the length of the curve is all measured along horizontal plane. Okay. Okay, so the last one is interesting one, the lowest point on the curve. So it's a sag curve, right? It's a sag vertical curve that we just designed, that we looked at. Now, the lowest point on the curve, so you can see, like, we are providing transition, right? So what's happening is that the grade was downwards, and then it kind of shifted, and then the slope started to reduce. And at some point, what would have to happen? If you're going from negative 3.5 to 0%, I mean, to positive 0.5%, what would have to happen somewhere along the way? Somewhere along the way, you'll hit 0, right? Somewhere along the way, you'll find that negative, because it's kind of reducing in magnitude. At some point, the slope will go to 0. So that lower, and then after that, slope will increase, because going from 0 to plus 0.5, because that's where you have to end up, right? So this slope is 0.5%. So you're going to start to increase that slope. Now, if you're going to increase that slope, what it means is that the curve will then rise from this point forward. So then your lowest point is the point where the slope of the parabolic equation is exactly 0, right? So that's the point you're trying to find out. Now, you've already found the equation, right? This is your generic equation where you've plugged in A, B, and C. So all you need to do is find the X value at which the slope of this equation becomes 0. Okay, so how do we do that? Let's do it. So we said the equation of our curve is this generic equation. And we're trying to find y equal to 1,000 plus 3.5x plus 1.6, 1 over 330,000 x squared. So I'm trying to find out, how do I get the slope of this equation. It's going to be dy over dx. And then if I do this, it's going to be negative 3.5 over 100. X will be 1, the derivative. And the derivative of this would be plus 2x over 30,000. That makes sense? Right? So we took the derivative of this equation. And then what do we do with this derivative to find the lowest point? For lowest point, right? For lowest point, what has to happen? Has to happen is this expression has to go to 0. The slope has to be equal to 0. So it's going to be negative 3.5 over 100 plus 2x over 30,000 equal to 0. And let's solve for this equation. Let's find what that x value is. Okay. By equating the slope to, right? So we're going to figure out the lowest point, the x value for the lowest point by equating the slope to 0. What is that? $525, let's call it 525. Is that what folks got? 525 feet? Okay, so I'm going to trust this number for now, 525 feet. First, let's kind of quickly do a sanity check on this number. Does that number make sense that it's more than 300? It does, right? Think about this. You're changing the slope at a constant rate. You're going from negative 3.5 to plus 0.5. You're changing the grade as constant rate. So it will take you longer distance to go from 3.5 to 0 than to go from 0 to 0.5, right? Because this is what's happening on the curve. As x goes up, your slope is going from negative 3.5 to 0. At 525 feet, it becomes 0. And then for the rest 75 feet, it becomes higher. It increases from 0 to positive 0.5. Okay, so that what has to happen. So this number looks correct to me, 525 feet. Now, how do I find the elevation of that point? If I want to find the elevation of this point, what do? You just go ahead and plug this back into this equation, right? The slope is 0, but then you can find the elevation of the lowest point. Of lowest point. Plug in x equal to 525 feet into the equation that we talked about, right? And what would that give me? You know, I just plug in x equal to 525 in the equation. 990.8 feet could be right. What was the elevation of PVI? 989. Yeah, that could be right. Right, so should be correct. 990.8 feet. That makes sense to me. And if somebody else got a different number, please let me know, because I'm not exactly sure what the number is going to be, but it should be in that ballpark, because the this should be the lowest point, and then because then we start going up from there. But you get that by plugging in 525 feet over here. Anybody can make mistakes. So if you're getting a different number, please let me know. Okay. All right. So now, so if you think about this, if you think about what we just talked about, the lowest point story, right? This lowest point story can actually tell you a much easier way to find, if you understand what that lowest point represents on these vertical curves, or the highest point if you're talking about a crest vertical curve. If you understand what it actually means, there is a much easier way for you to figure out what that lowest point x value is going to be. Much easier way. Let's think about that easier way here. And we're not going to solve the problem, a lot of problems right now with this. We'll come back to this question. But since we talked about this lowest point, I want you to have a much easier accessible way to figure out or playing with the lowest point a little bit. 10. So the lowest point will come when you have completely neutralized the initial grade, right? When you have completely neutralized the initial grade, right? And you know at the rate at which you're changing the grade also, right? You know at rate at which you're changing the grade. You're changing the grade. How much is the change of grade in this problem? You're going from negative 3.5% to positive 5%. So your total change in grade, so if you can figure out the total change in grade is what? D2 is like 0.5% minus 3.5%, right? So that means you're changing the grade overall by 4%, right? Using this curve, you're achieving a grade change of 4%. Does that make sense for everybody, how we got this? Now, let me ask you this. You're doing this over what length? You're changing the grade by 4% over what length? 600 feet, right? You're changing the grade by 4% over L equal to 600 feet. So I ask you a simple question. How much length are you using? Because remember, the grade change is happening at a constant rate. The question is, how much length are you using to change the grade by just 1%? You can figure that out, right? You're using 600 feet to change the grade by 4%. So you can tell me how much length are you using to change the grade by 1%? 600 divided by, if I want to find out, see, you're changing the grade by 4% over L equal to 600 feet. My question to you is, because it's a constant rate change, right? It's the slope is changing at a constant rate. That's the whole story of the parabola, right? The grade changes at a constant rate. 600 feet to change the grade by 4%. My question is, how much length is used to change grade by 1%? I'm thinking faster than I'm writing this. How much length is used to change the grade by just 1%? Yes. 150 feet, right? How did I get that? I got the total length. I divide by the total change in grade. So I can get that by doing 600 by 4. And that's 150 feet. So I'm using the 150 feet length to change the grade by 1%. Now think about the lowest point. Think about the lowest point. What's so special about the lowest point? Lowest point will have the slope 0, right? What does that mean? How much grade would you have changed if you need to arrive to the lowest point? 3.5%, right? You would have changed the grade from negative 3.5 all the way to 0. So you always, in any vertical curve problem, if you want to get to the lowest point or the highest point, if it's a crest curve, you would have, if you want to get to that 0 slope point, you would have always reached the point where, you basically neutralize the initial grade completely. That means you've changed the grade equal to that initial grade amount, which in this problem was 3.5%. So if I want to find the lowest point on the curve, so the other way of finding the lowest point, so that means the lowest point will be located, the lowest point will be at 150 times 3.5% or 3.5, right? So if you do this, 3.5 times 150, you will get that 525, right? Does that make sense to everybody, what we did here? We found out what is the rate of change of slope, right? How much length are we using to change the grade by just 1%? And then you use that rate to multiply that by how much did you change the grade. The lowest point, X value for the lowest point will be 550 times 3.5. And that's your G1, right? So that's your initial grade magnitude. The magnitude of initial grade, because that's the grade you're neutralizing to reach that lowest point. So this is obviously, this is much easier to solve, right? You can easily find out. In fact, I have a slide on this a little bit later, and I want to bring that up here. So if I come here, after a few examples, I have and I'll talk about this in a second. So yeah. So let me see and move this slide up. Okay. So this is the slide I sometimes use, and so if I go to so this is the way we think about this. So we say this value, this how much length is being used to change the grade by 1%. This is what we call the capital K value for a vertical curve, capital K value. Okay, how much length are we using to change the grade by just 1%? It's called the K value. And that K value you will see right here. Okay. Capital A value is magnitude of G2 minus G1, right? So how much the total change in grade you're doing, right? How much is the total change going? So that's your A value. And X is the distance from PVC to the high or low point. If you want to measure that, you can just do 100 times K times G1 magnitude. Now I plug in these hundreds here because I want you to put capital A value in feet per feet. And I want you to get the G1 value also in feet per feet. But you can see that as long as you keep your units consistent, you can work without that 100 in the formula. But this 100 is there so that you're measuring. So that 100 is there because you're trying to find out capital A value is the total change in grade in the vertical curve. And then G1 is the slope of the initial tangent. And then the approach grade at the beginning of the curve. And this 100 factor is there. So you're plugging in A value, capital A value, and the G1 value in feet per feet and not as a percent. Okay, so that's what's happening here. So instead of saying, so I would say 600 divided by 0.04 times 100. If you were to apply the formula that you see on the slide right here, you wouldn't just divide by 4, you'll divide by 0.04 times 100, right? Because that will be 0.04 will be the correct unit in terms of feet per feet. Okay, so it's the same. The end result will be the same, of course, right? So I just did 4 because I was just kind of dealing with percentages here. But if you want to, I want you to plug in this formula as capital A value in feet per feet and G1 value also in feet per feet. So that these 100, correct the equation, right? So I just want to make a note here that you want to write down. I want to make a note here, the enter values for capital A and G's and grades in feet per feet, okay? Because if you do that, then this 100 will basically take care of that. This formula that has these 100, they will start to make sense. But the overall idea is the same. The overall idea is that, you figure out the K value, how much length is being used to change the grade by 1% for any curve. And then you multiply that by the initial grade to figure out the high or the low point. High point for the crest curve, low point for the sag curve. Okay. Let's do a couple more examples here. Okay. So I have 2 more examples, but let's do. The second example is there is an equal tangent vertical curve to be constructed between grades of -2 and 1%. Again, sag vertical curve, but that's okay. It doesn't matter. The PVI is at station 110 plus 00 and elevation 420 feet. Now be careful. They give you the PVI's elevations and PVI is station. So just be mindful of that. The point that's given to you is PVI. Due to a street crossing the roadway, the elevation of roadway at station 112 must be 424.5. Right? Whatever you do, the elevation has to be 424.5 at 112 plus 00. And these types of design problems exist all throughout. They show up in the PE exam all the time, and they show up in the real world all the time as well. Because what happens is that we're not building infrastructure in a vacuum, right? We are building infrastructure over what already exists. So there is always constraints of what we need to do. And in this case, the constraint is that at station 112 plus 00, your elevation has to be 424.5 feet. Okay, and then it says design the curve. And what I mean by design the curve is basically get me the length of the curve and get me the parameters of that equation. I mean, if you get the length of the curve, that's the most important thing. And get me the elevation of PVC and PVT and all that good stuff. Okay, so now let's think about this problem here. See what's given to us, and we can draw this out as well. So let's think. There's an equal tangent vertical curve between initial grade of -2 and +1%. So you got -2%, right? So you got, let me start here. -2% grade, and then at a +1% grade, right? This is the PVI point, the intersection where the two tangents must have met. And then let me draw out this curve here. This is my PVC. This is my PVT. PVI is at station 110 plus 00. And we always kind of PVCs are starting point. So we know that the stations are increasing as I move from PVC to PVT. Right? That's the convention we always use, right? So can I find out? And then I know the elevation here is 424.45 feet. And I'll avoid using the term y equal to 424.5 feet because I want to reserve the term y or the variable y for points on the curve. Okay, so that's why I'll not say y equal to 424.5 feet. I'll just write out the term elevation because otherwise it can get confusing. Yes.
Yeah, another 420.
Oh, PVI is at, oh yeah, PVI is at 420. Thank you. Yes. So PVI is at 420 feet. Okay. Yeah. Thank you for pointing that out. Of course, on purpose, just to make sure who's paying attention, who's not, right? So 420 feet. And then, so elevation, we'll call it 420 feet. Now, let's see if we can, because remember, like our curve equation looks like this, right? Y equal to A plus BX plus CX squared. This is what the curve equation looks like. And if I want to find my curve equation here, if my curve equation looks like this, then I need to find what A, B, and C are. And remember, in our sheet, A is the elevation of PVC, B is the initial slope, C is the G2 minus G1 over 2L, right? That's what it is. Now, we don't know length of the curve yet, so we won't know that. So we have to solve for the length. So if somebody says design the curve, the most important thing you need to find is what's the length of the curve, right? So you need to find the length of the curve. Now, so basically L in this problem is going to be an unknown. So if I want to take like this, write this down, this is going to be the L value. And I actually don't know that because that's the problem, design the curve, right? I don't know the length of the curve. Now in the tests, I will be very explicit about what I'm looking for. I will not just leave it at design the curve. I will ask you specifically what I'm looking for. But typically when you say design the curve, you're looking for the length of the curve and the elevation and stationing of key points, basically, right? But I will be more explicit in the tests. But first thing I need to find is the length of the curve here. So let's think about this. If we don't know the length of the curve, so let's see what can we find. Can we find A in this problem? Is that given to us? It's not given to us at all. Like we don't know the elevation of PVC. We know the elevation of PVI, which is nice, but we don't know what L over 2 is going to be because again, our curves are always equal tangents. So we know it's going to be L over 2, but we don't know what that length is. Okay, so we can't find A directly. Do we know B? We're kind of doing a status check, right? What can we find from here? B. We know B because B is just G1. And in this case, it's going to be 0.02, or you can say 2 over 100, 0.02. So that's good. At least we know B. And remember C, if you remember the formula from the previous slide, is G2 minus G1 over 2L. And G2 is 0.01, right? 1% grade minus 0.02, G2 minus G1 over 2 times L. And again, I don't know L, but that's where I'm at, right? And so now this A, so among the A, B, and C, I only know B fully. I don't know the value for C because C also has a length value in the equation, and I assume the length to be L. Now, can I find A value, the elevation of PVC, not directly, but can I find it in terms of L? Yeah, so that's good because if I can kind of convert all of these A, B, and C in the form of L, the length, then maybe I'm getting some. Maybe I can create an equation where I only have one unknown and I can solve for the length of the curve. Okay, so let's think about this. What's going to be the value of A? It's the elevation of PVC. We know that. And how do I find the elevation of PVC in terms of L even? I know the elevation here. Is there enough information for me to find the elevation of this point? I do. I mean, in terms of L, I can at least find it because I know that the grade is negative 2%. And I'm going what? PVI, and I'm going up the distance L over 2, right? Because L over 2 is the horizontal distance. So how far higher I would go is I can find it. So I could say elevation of PVC will be elevation of PVI plus L over 2 times G1, right? And why did I do plus? I should say probably minus here, right? Because I'm going backwards, right? So elevation of PVI minus G1 times. So this is a generic formula, right? So if I do elevation of PVC equal to elevation of PVI minus L over 2 times G1, because I'm going L over 2 backwards. But when I plug in the value for G1, I'm going to plug in negative 0.02. Okay, so I'm going to say elevation of PVI, which is 420, minus L over 2. I don't know what L is. And G1 is 0.02, but negative value. Right? And then that way, I will get 420 plus 0.01 L. Does that make sense? What we did here? Remember the negative and positive signs? To get the elevation of PVC, you subtract from the elevation of PVI the L over 2 times G1. But because G1 is negative, PVC is going to be a higher elevation point, as it should be according to the sag vertical curve that I just showed you. So this is good now because if I know, so I can write this equation in terms of L now, y and x, y, and L now. So y will be equal to elevation of any point on the curve must be equal to A, which is 420 plus 0.01 L, right? So this is my A, plus bx squared. B is just G1 minus 0.02 bx, right? So x, 0.02 x plus c x squared. C will be what? C will be G2 minus G1 over 2L, which is, if I solve it, it will be 0.03 over 2L times x squared. So A plus bx plus cx squared. And remember now, I took the value for A, B, and C, plugged that into the main equation. and I have these term y, L, and X in here. Right? So I have an equation, the generic equation all set up now. Right? The generic equation is all set up. Now I need one independent point on this curve so that I can plug in the value for X and Y and maybe potentially solve this problem. Right? Because I need to find the length. What is that point here? Do I know one point?
Street crossing.
Yeah, the street crossing, right? The elevation of the roadway at station 112 plus 00 must be 424.5. So I know Y has to be 424.5 here. At that street crossing, Y has to be 424.5 feet. So I can plug Y value in. I need to figure out what is going to be the X value at that point. Would X value be, let me ask you this. Should I plug in X equal to 11,200 because one station is 100 feet? It's 112 station. So 112 times 100, 11,200 feet. No, that's not how we define X, right? X is not defined based on the stationing. The X value is defined as positioning relative to PVC, horizontal positioning relative to PVC. So what would be the X value for that point at station 112? So all you need to now figure out is what's going to be my stationing what's going to be my X value where the stationing is 112 plus 00. And that's a tricky question to answer, but there is enough information here for you to do it. Yes.
Is it over 2 plus 200?
That's exactly what it will be, L over 2 plus 200. How do I get that, right? So I know that the station is 110 here, and I know that the station always increase from left to right as I go from PVC to PVT. So that 112 point will be located somewhere here, right? Because it's going to be to the right of, from where you're looking, to the right of PVI, because PVI only has a station of 110. So this will be my station 112. And because its station is 112, we know that the horizontal distance is only 2 full stations between PVI and that point, right? So we know that this distance here has to be 200 feet, right? So that point of interest where the street crossing is, it's 200 feet away, okay? And we know that this has to be L over 2 because it's an equal tangent vertical curve. That's how we always design it. So from PVC, what's going to be the horizontal positioning of this point? It's going to be L over 2. It's going to be L over 2 plus 200, right? So your X value, so Y will be 425 feet, X equal to L over 2 plus 200. Now, if you plug that in there, X equal to L over 2 plus 200 and Y equal to 424.5 feet, do you have enough information to solve for the length of the curve, right? Because it's only one equation. It might be quadratic. I don't know. We'll have to see. Probably not, because this should cancel out, but we'll see. But you can figure that out, whatever that is. But you can plug in X equal to L over 2 plus 200, Y equal to 424.5, and just plug and chug and try to see if you can solve for the L value. That makes sense, right? So all you did was you had your basic equation. You use the constraints of the problem to kind of find out all these values of A, B, and C first, or not the constraint, but the given information to find the A, B, and C values, the parameters of your equation first. You didn't know them directly, but you kind of brought them along in the form of just one variable, one unknown quantity, L, right? And then you plugged in one known point on the curve, which was also somehow you had to set that up in the terms of L. You kind of got everything in terms of one variable. And now you're basically ready to solve that equation in L, and you will get the answer. Make sense? Right? I'll let you find that answer. I think, I don't know what the answer is right now. But go ahead and find it. We have maybe a couple of minutes. Maybe some of you can find it. So tell me what the answer is for this one. next couple of minutes, and then that'll end the class. But in the next class, what I'll do is I'll talk about another approach to solving this problem like this, which is a little bit, chances of making mistakes are a little bit higher, but computationally it's much more easier, right? So you will be able to solve it much more easily. But tell me what the L value is going to be. So this X is not correct, right? This X equal to 11,200 will be incorrect. X will be L over 2 plus 200, and then you can solve for L. If anybody has answer in terms of L, I'll take that. Otherwise, we can come back in the next class and talk about what the answer for L is going to be. Okay. Any values for L yet? It should not become a quadratic if I'm remembering it correctly, because this is a divided by L expression. All of that should take care of itself. So the key things to remember, from the lecture today, once you've solved for L, and anybody has the answer yet? Don't be shy. I mean, it's okay. You make
1,347.
1,347 should be correct. It rings a bell from last quarter or something. So 1,347 feet. Yeah, I mean it's probably correct. So check this answer. If this sounds correct, we can pick up from here. But I think the key things to remember is that equation form, how to derive A, B, and C, given the formula, and then PVI is not a point on the curve, and then the easy way to derive the lowest and highest point on the curve. And then we'll talk about how can we solve example 2 in a little bit easier way in the next class as well. 1,347 feet, we'll remember this answer. Okay?
You get it?